the cloud.
Okay. Hi. Good morning. Thank you all for joining us today. I am going to be your host. My name is Amrita Zadhan for some of the new members who have joined us this month. And today we are joined by two really impressive speakers, Alex Gurvich and Peter Teuben. So Alex is a PhD student at Sierra Northwestern and works on fire galaxy formation simulations to study stellar feedbacks, and is most interested in how supernovae from dying stars can prevent the formation of new stars by driving turbulence in the ISM. Alice has helped create Firefly, which is an interactive, web-based and publicly available visualization platform that he would be talking about today. And in fact, has also won the Sierra Visualization Award last year for his impressive work. So Alex, would you like to go ahead and take the stage, please?
Yeah, that's the best introduction I think I've ever gotten. Thank you. Okay, everybody can hopefully see my slides now.
Yep.
I'm gonna move you there. Perfect. Yeah, so that covers a lot of ground that I was going to talk over my title slide on. So I guess I'll just jump right on in. I do want to mention that Firefly has been a work of passion and love and escape from some of the stellar feedback work that I mostly do in partnership with Aaron Geller, who's research faculty at Northwestern and who I saw is also on the call, so who will probably be helping me out in the questions. And I also wanted to highlight that Aaron and I just got our paper on Firefly accepted into app.js. And so the most up-to-date version we're going to put up onto the archive any day now, once the proofs are all through. So Firefly, what is Firefly? So just the vital statistics in one slide. Firefly is a web application for visualizing your data. It can make 3D scatter plots, 3D quiver plots, or even like a 2D histogram projection that you can spin around, fly through, pan, zoom, whatever, the whole shebang. But crucially, it's all running inside of a web browser, and it's rendering client side, so on your laptop in that tab. And we spent a lot of time optimizing it so that you could get interactive frame rates for even 20, 30, up to 40 million particles, which really limited not by the frame rate, but actually how much RAM Chrome is allowed to take up. Like Chrome gets a lot of flack for like eating up all your RAM, but this is the one time that I really wish you could give it more. That's actually hard-coded limit. But anyway, I digress. Firefly can also filter, color, or rescale the points by any arbitrary scalar fields that you attach to them. So like the temperature, the density, whatever you'd like to come up with. That's in terms of the features, some of the vital statistics. How Firefly is written, the web application is in JavaScript, uses the 3JS library for some primitive objects to create the scene and render it. We wrote some custom shaders that help create some of the different display modes. The one thing that's really interesting about Firefly is that it has a user interface that's built programmatically. So one thing I'll show in the demo very quickly is that each element of the user interface has its own URL that you can flag to be disabled. So you can individually turn off different pieces to custom tailor a visualization for different audiences so that people don't end up messing around with things that you don't want them to. And maybe most importantly, there's a convenient Python front end so that you can create new Firefly visualizations or host and explore them on your local machine without having to host them on the internet. That I'll talk more about near the end. So, okay, that's kind of the one slide summary here. I've just lifted figure 1 from the paper to demonstrate some of the different rendering modes. These are screenshots taken directly from Firefly. And what I'd hope to emphasize here is the flexibility of Firefly to display all sorts of different data. I like to say that if you can get your data into a NumPy array, you can get it into Firefly and then visualize it, host it on the internet, and do all of the pieces as long as you can get it into NumPy. That's really the only constraint. But, you know, in terms of tying it to astronomy, one thing that I really wanted to emphasize is that it's not necessarily just for simulation data, though, of course, that's what I spend most of my time thinking about. You can also stuff in some observational data. And so the bottom row shows like the Sloan Digital Sky Survey catalog for different galaxy classified with Galaxy Zoo. And then one thing that, you know, Aaron and I worked really hard to make happen was to stuff all billion stars from Gaia DR3 into Firefly using a progressive rendering scheme where only the stuff that's actually in the camera frame is ever loaded from disk, so that you're never hitting that upper RAM limit that Chrome enforces on you. And as far as we know, Firefly and this progressive rendering scheme is the only way that you can interactively visualize the entire data set and fly through it and load the data as you need it. But, you know, if somebody else has done it, I definitely want to hear it and hear about it so that we can compare notes, because there's all sorts of things that we want to try and improve and make better. So that's great. You know, I've showed you some static images. One thing, and then I didn't check. Okay, good. I did hit optimize for video clip. So Firefly can also export animations and videos. So it can record your motions, like whatever you're doing, and output it to a GIF for you. So that's what I did here. I was just panning around some objects in some snapshots from the fire simulations. But, you know, most importantly, I've shown you static images. I've shown you GIFs. You know, Firefly is all about interactively exploring data. So I'm going to attempt to do a live demonstration. Hopefully everything goes well. So, okay, here I'm showing a high resolution data set from the fire simulations in the column density projection mode. The interface is collapsed up here in the top left corner, and it has this cool state swapping situation where different aspects of the interface are hidden or collapsed depending on what you want to see, so that everything stays nice and condensed. Right now I'm just spinning, zooming, etc. You know, we can zoom out, but we can also enter the fly mode. And so now, if you're good, you can fly around. Let's pick something to go fly to. I think that there's a satellite galaxy somewhere over here. Also don't want to spend too much time because I have a lot of ground to cover. Okay, yeah, let's go over here. Ooh, wow. And so there's a trick here where you stuff your face into the satellite galaxy, you drop an anchor, switching back into our trackball, orbit controls, and now you're spinning around this other little satellite galaxy. And you can see, you know, from its perspective, what it looks like to fall into a Milky Way mass halo. One other thing, oh, that's not the one other thing I wanted to show off is, so this is all static moments in time, but you can, let's turn off some of the other components. These are called particle groups. I'll go into that in a second. And then you can animate the velocities to get, oh, that's maybe a little too fast. There we go. There we go. So you get kind of like a streamline effect. And so now what we're doing is we're extrapolating along individual velocity vectors. So this isn't integrating in time necessarily. This is just, you know, x equals x naught plus v times dt. But one of the things that we're really excited to do is have like time series of data and then actually interpolate between them. And so here, another feature that we're showing off is the quiver plot mode. So here there are a bunch of arrows. We're coloring them by the magnitude of the velocity. And then last but not least, one thing I wanted to show is that you can have multiple data sets that you can switch between in a single Firefly setup. So here I have the same simulation at different times. And then it's going to load up the data, build the UI. Wow, beautiful spiral structure, amazing. And again, you can turn on and off different components. So here I have stars sorted by how old they are, for example, all predefined. And with the state, as you saw, the stars all started off, you can set all that up in the settings. So, okay, I think I'm going to go back to the slides. Come back, please. Thank you. So, okay, so I showed just a handful of features because I really wanted to move quickly through that. Here's a mostly exhaustive list of the different things that you can do in Firefly sorted by complexity. One thing that I wanted to highlight that I didn't get, or a couple things that I didn't get to demonstrate, but I did want to highlight was you can use it inside a Jupyter notebook by embedding it into a notebook cell. So you can do your analysis and your visualization in situ right next to one another. It's actually VR ready. If you have Google Cardboard, you can load up a visualization on your phone, strap it to your face, and then start looking around. So that's exciting. And then you can also, so I said everything was rendered client side. So you can also, there's a mode to render server side and stream the view from one computer to the other, or to still render client side, but have multiple people interacting with the same scene and then being able to mirror the view and dragging and dropping and spinning and whatever. And then I actually did get to show off the streamline thing, so I should have unhighlighted that. Okay, so I showed a couple of examples. We have a couple more in our gallery. If you do decide that you want to try out Firefly, please drop us a line and we'd be happy to feature you in the gallery. You know, we would love to fill this out with all sorts of different examples to show off the flexibility of Firefly and what people are doing with it. One thing that isn't shown here is you like hover over it and it'll give you like a little description of each of the thumbnails. And we also have a comprehensive documentation that helps you get started working with Firefly, both in terms of how to use it, what the different features are, how to enable them, etc., but also how to make your own Firefly visualizations, starting from a minimal working example that doesn't even have real data. You're just making like a random cube, all the way up to making the versions of the stuff that we have in the gallery. So all of the different pieces, we have like cookbook recipes for how to make those. Okay, so that's all I want to talk about in terms of how Firefly, you know, what is Firefly and what are its features. I want to use the rest of the time to talk a little bit about how Firefly works under the hood. And in particular, I want to draw just like a big picture of what a Firefly workflow looks like from start to finish. So in the beginning, there's a user and their data, they're in the void, and they would like to explore it. Firefly enters the equation with two different pieces. So there's the Python front end that we call the data preprocessor, the PDPP, and then there's the web application itself. So the first step for a user is to take their data, put it into the PDPP, for it to translate that data and generate reformatted files that are in a Python, a binary format that Firefly can understand. Then the next step is to bring in your favorite web browser. So any modern web browser should be able to run Firefly as long as it has WebGL capabilities. So things like Chrome, Firefox, Safari, whatever. I don't know if it'll run on a smart fridge, but it does run on a phone or an iPad. I don't know if it runs on like a PlayStation or something. You might try that. But anyway, one thing that I will mention is that if you have Apple Silicon, then you have to enable hardware acceleration because that's disabled by default. And each browser has their own configuration flags that you need to do that. We have an example in our documentation. You can find it on the landing page of the docs for Chrome, which is what Aaron and I use. So that's what we're most familiar with. But anyway, okay, web browser files. Web browsers get files, they retrieve them from servers. So those servers can either be remote, like living on the internet, or they can be local, just generated by your own computer and only accessible by people on your local network. And because that's kind of hard, most people don't know how to upload stuff to servers or run local servers on their computer. we added the ability for the Python front end to also create local servers with just one-liners, or even if you set up a GitHub OAuth token for your machine, then I put together a little script that will create a new GitHub repository, enable GitHub pages for it, push your version of Firefly along with all of the data, and then host that on the internet, give you back a URL so that you can share it with people, all with just one command. I think it's like copy source to target, enable GitHub pages equals true, or something like that.
Alex,
and,
just wanted to let you know you have 4 minutes left.
Perfect. Thank you. You can also skip the step of translating your data and reduplicating it in a Firefly format by sending files virtually directly to the server. So everything is just stored in RAM if you're running things locally. There's really no way, like you got to upload it to the remote server if you're going to do it remotely. And then the fun begins. The user is able to access the Firefly web application, and the web browser launches the app, loads in all the data, renders stuff to the canvas, the user sends commands back and forth, etc. So, okay, that's the big picture. With the couple of minutes that I have left, I want to try and zoom in and go through how the PDPP works, and then the web application itself. So how does the PDPP work under the hood? The PDPP is split into 3 parts. There's the stuff that helps with that server thing, so either hosting locally, or we have the command line interface, which will help you upload your Firefly instances to the internet and manage their source files. And then what I want to focus on today is this data stuff here that does the actual translation piece. Data sets in Firefly are organized using a manifest file, filenames.json. It's what it sounds like, a JSON file with a bunch of file names in it that point to the data and settings for that visualization. That dropdown that I demonstrated, you can create that automatically by just having a startup.json file that contains multiple file names.json, and then you get that dropdown. Or if you use a query string in your URL, it'll just go straight to that index. To create file names.jsons, you'll use reader class instances from the PDPP. And reader class instances contain settings class instances, which contain things like the application settings, so where the camera is, what, whether things should be like full screen, whether the UI should be expanded or not, whatever. And also settings for each of the individual particle groups, like what the filter and color bar limits are, whether a certain particle group is enabled, etc. Then there's the actual raw particle data that gets stuffed into particle group class instances. And when you're ready to actually output, the particle group instances will automatically chunk and serialize your data into the binary format that Firefly uses, so that you don't have to think anything about it. And then, of course, you can have as many particle groups as you want into a reader, and that's how you have those different panes in the UI that you can like toggle whether different components are on or off, is by using different particle groups. And I know that I'm moving fast, so I just want to re-emphasize that we have tutorials that walk you through each step of how to use one of these different class instances at our website, fireflybiz.com. Okay, and then I think I should probably have like a minute left, so I'm just going to go ahead and briefly show the slides for the web application. The web application is split into 2 steps: starting everything up, loading the data in, and then the actual render loop. So start up, you load all the data, read it in, create the objects that you need, generate the user interface using the URLs that I mentioned to disable individual elements of the user interface. And then in rendering, you synchronize the UI with the data model underlying the app, update all of the primitive objects, and then actually pass things off to the shader to do all of your rendering. So I hope that I have given you a good idea of what Firefly is, and maybe you're interested in trying it out for yourself. There's a couple ways that you can do that. You can just go ahead and grab it off pip. I pushed a recent version, I think like yesterday or the day or before, somebody had raised an issue on a typo. It is my bad. You could grab the source directly from our website at fireflyviz.com, has a link to the repo. And we're also integrated with YT. So if you already use YT, it turns out you didn't even know it, but you could export to Firefly just by taking your data region. And I think it's literally .export to Firefly. So that's my spiel. I guess I'm happy to take any questions with whatever time I have left. Thanks.
Oh, awesome talk, Alex. I see Peter has a few questions in the chat already.
Did we want to do questions at the end of both talks like we normally do?
If we want to do one or two quick questions, we can do them now, or we can just like do them after the
Sure,
talks.
we can do that now as well. Yeah, so I think I see kind of two main questions in the chat. So one from Michael. He asks, he says, JavaScript is traditionally not taught to astronomy students. What is your advice for students wanting to become proficient enough in JavaScript to do interactive visualization?
So,
thank you for the question,
I think,
Michael.
Yeah, that's a great question. So I have a couple of thoughts. So number one, you certainly don't need to know JavaScript to do interactive visualization with Firefly. And I don't think that you need to know JavaScript to do interactive visualization just generally. I think if you're using existing software to do interactive visualization, that you can use the features as it is. Now, if you mean like if somebody wants to contribute to Firefly or some other project that's using JavaScript, maybe a broader question is, how do we encourage students to contribute to projects in languages that they don't necessarily know, but they're excited about the project itself? And I think that that's a hard question to answer, and I don't have any specific advice except for project maintainers to be really good about identifying issues that somebody that is not very familiar with the language can approach and use that as an on-ramp. And so like being really good with the tag, like good first contribution or whatever, I think that's the advice I would give to maintainers. But I think if you're an astronomy student and you want to do some task, I would not recommend just going off and learning JavaScript. Or like, Code Academy thing, that's the best one.
Okay,
I hope
awesome.
that answers the question.
Yeah, thanks, Alex.
Yeah. Okay. So with that clarifying question, we can move all of the other questions towards the end of the discussion. Thank you again, Alex. And so before we move on to our next speaker, I just wanted to quickly share my screen to show you all something, which is that our very own Alice Allen was nominated as a 2023 AAS Fellow. So many congratulations, Alice, for her legendary and amazing work, deep knowledge and advocacy for ASCL, and generally making open source software available for all of us and motivating all of us to do that. Congrats, Alice.
Thank you very much. I was very surprised to get that email, and I'm still very surprised that I got that email. So, but once it appeared on the website, I figured there was no backsies. They couldn't take it away. So that's when I started believing it. Thank you.
Yeah. So, and with that, we can move on to our next speaker today, which is Peter Teuben. Thank you again, Alice. So Peter's main interest is in radio astronomy, galactic hydrodynamics, and community software development, such as NEMO, about which Peter will be talking about today. So he has a lot of experience and in development of community software for visualization and analyzation of N-body and related simulations. So if we also want to probe Peter about some of those discussions towards the end of his talk, that would be great. So Peter, talk, if you would like to start and share your screen, please.
Peter, I think you're still muted.
Yep, of course you're right. So I'm going to look at the other screen because that's where my display is. All right, NEMO. So this was my first postdoc project. I did a lot of software for radio astronomy already in my graduate students, but I never really did n-body simulations, despite that my advisor was an n-body simulator. And so when I got the opportunity to work on n-body work, I gladly took that. So we developed this program called NEMO. Not everybody must observe was the acronym that somebody came up with, but it's not meant to be an acronym. Here's a couple of pictures that I'll show later in the talk. And I also wanted to recommend or that you learn about the future of astronomical data infrastructure, which is a conference that's going on this week at Flatiron. This is what I want to cover, what NEMO is. I'm going to highlight some of the features of NEMO then and now, talk a bit about reproducibility that came out of the meeting that we're having this week that I'm skipping out of right now. And then at the end, do some demo and some visualization, which actually is very similar to the talk that you heard right before here, using a program that was derived from NEMO called GL-NEMO 2. And you saw the repo link there. So here's just a couple of examples, an n-body simulation of a galaxy that forms a bar. And then what you can do is you follow a particular star in that simulation and you look what the orbit looks like. For those who work in bars, we'll see that this is an X1 orbit that suddenly became an X4 orbit. The study of orbits using that GL-NEMO 2 program. You can import simulations. Here's an import of the Eagle simulations, but all the post-processing, the images that you see in DS9 were done with NEMO. So NEMO doesn't only do n-body simulations, it can produce CCD images, FITS images if you wish, and then import them into DS9, for example. Here is one of those galaxies in that simulation, folded out in that cube, the particle distribution, and a little grayscale simulation of what the H1 would look like. Here's a velocity field of a galaxy, also made with NEMO. And as I said, in NEMO, you can have particle distributions as well as images and image cubes from which this velocity field is derived. So historically, where did we start? It started in 1986 when I was on my postdoc. And at that time, I had worked as a grad student with Gypsy. And there were a few other data processing systems, mostly for either radio or optical, and probably APES and IRAF are the most well-known from them. But there was nothing for people in theory. And if you looked around, my advisor, myself, and other people that I knew, they all wrote their tools themselves. And when they changed postdoc, they got to a different computer system, and the graphics wouldn't work there. So they rewrote all of their tools so that the graphics would work. And each of these n-body simulators in my area would do that all by themselves. So with Pete Hutt, Josh Barnes, and myself, we decided we were going to write a package similar to APES and Gypsy, what I worked on, and so forth. So that became NEMO. Now, that was 1986. That's a little while ago. So the fact that it still works, we can really say it's been long-lived and it's legacy code. It was initially developed on Sun OS. These machines barely exist anymore, but we've evolved through many, many revisions of Unix, and now it runs both on Linux and on Mac OS. The initial development was actually all in Kernighan and Ritchie C, if that means anything to you. So that code on most compilers doesn't even compile anymore. So you can already see in all of the years we had to do a lot of work to prevent this thing called software rot. Some of the highlights when you work with NEMO, it is just a toolkit. It has a library, and you compile your code with the library, and you create a whole bunch of binaries. Very classic, just like the stuff that was built in '86. You use scripting to write your simulation scripts. The command line user interface is a very generic keyword equals value that describes itself, and that has very interesting repercussions I'll talk about in a minute. That we had to invent our own data format because FITS wouldn't work for us. HDF didn't exist yet, so we wrote our own binary type tagged hierarchical data format, which effectively, if you look at it, is a binary XML. If you think about it that way, that's effectively what it is. What's very powerful that all the tasks that I mentioned, they can pipe their data in Unix style, so you don't have to write files on the hard drive all the time. And that used to be much more important than it is now that the hard drives are so fast. one of the most powerful elements that we have in NEMO is this thing called dynamically loadable objects. As opposed to writing an expression parser, a little program writes the C code, loads it into memory, and puts a pointer to that function, so that when you have a billion particles, you don't have to do a parser through it, but it just runs the code in binary. Potentials, which you have to use for orbit calculations, have the same idea. You load that in a function dynamically, and you can tell it, this is my function, and you parameterize it and run orbits in it. Otherwise, we use various standard Unix tools. The man page, for example, for plotting, the thing that I mentioned that so many people struggled with in the past, we defined our own interface, yet another plotting package. And it has to be implemented in your particular graphics thing. So we have one for pgplot, we have one for plplot, and one for native PS if nothing else works. What are the highlights if I now look back? What are the things new now that we are here? We now use Git, we use read the docs, the LaTeX manual is now converted to RST. We tag all our codes that we have in NEMO with an ADS bib code. I'll get to that back in a minute. There's a couple of interesting tools that make it very easy to compile new programs, to make plots from tables, reproducible, and so forth. There's some regression benchmarking in it. We have a standard install method. And most importantly, at the bottom, we have lots of third-party dynamics codes. We didn't modify them. We put an extra little NEMO shell on it, so it looks like a NEMO program, but it runs that particular code from RSAT, for example, or Van Albada in the background. So a few things on this user interface. That keyword equals value was very predictable. It can describe itself, so it can actually, using a little program that we call tkrun, provide a GUI interface to a particular program or shell. That makes it very easy to self-discover and go over a parameter space and slide around your parameters and see what comes out. This is an example of that, where a script generates a model with a cone in it, and it produces a velocity field, pops in the diagrams in DS9, blah, blah, blah. I think we went over that. Graphics, I want to highlight that GL NEMO 2. Again, it's just one of the systems that we don't use with YAP, but it's independently developed. Install, I'm going to skip over that. I think we went over that already. This I want to say a little bit about the third-party legacy code. I mentioned that we often import them as is, and then we put a NEMO command line interface on it. We also add the ADS references, so later you can then provide a little table of all the codes in NEMO where the papers that belong to that code are. The most fun thing I did earlier last year was Sebastian van Herner's N-body code. He wrote arguably the very first N-body code on a computer in 1960, but he also developed his own random number generator, which is really fun to read in the literature. So we reproduced that. It's really kiddie. It's really great fun. RSAT later publicly put his code on the web, which we have in NEMO, and it's called First N. So the very first N-body code that was written for a computer is also in NEMO. Fun to play with. So this is that example of codes and papers. Of course, when you go to archive, and ASCL gave us a lot of power to find out what the codes are and what the papers that belong to it. But if you go in NEMO, we have this ADS tag that we put in papers, and then we automatically harvest this table that you see below of all these public codes and where the paper is that belongs to that. And all you put in is a little add ADS tag, and it harvests by itself. A few words about genealogy. NEMO doesn't stand by itself. When NEMO was developed, we really did what we call collisionless dynamics. And there is another field in N-body called collisional dynamics, which is much harder. And a follow-up on NEMO that was independently developed is called StarLab, out of which came ACS and out of which came AMUSE, if you wish. So AMUSE is really at the top of the pyramid in that sense, that really combines all of the ideas of NEMO, StarLab, ACS, and so forth, and the third-party tools. And AMUSE is really a Python kernel that runs all of these ancillary codes. We also have a siblings like Zeno was derived from NEMO by Josh Barnes. We have related codes like GalPy, for example, uses the NEMO potential descriptor that I mentioned earlier. Gala and YT in particular are interesting to us because they have many ideas that we share. And we had to adopt a number of packages, libraries that we use for various disk file I/O and plotting. Now, the last thing I wanted to show was this thing that came up that also exists in NEMO. We do a reproducibility check. Does the code still produce the same numbers from the same codes? And so as we discussed this at the meeting this week, it turns out there's actually 3 different concepts: repeatability, reproducibility, and replicability. But it turns out that's the ACM definition that you see there. If you go to the NAS, those are actually reversed if you go to that link. They mean, so the reproducibility and replicability are actually reversed in their definition in ACM compared to NAS. A demo. How many more minutes do I have?
No.
You're muted.
Hi, can you hear me?
Yes. How many?
So you have like at least 10 minutes remaining,
Oh.
like 8 to 10 minutes.
Oh,
Yeah.
good gracious, that's way too much. But
Yeah.
I'll do
You
the
can,
demo.
you can take as much as you want or as little.
Yeah.
So
Oh,
Yeah.
No, I forgot that slide. Yeah, this was the demo. Now that I have a bit more time,
yeah.
I can do this guy. All right, so we're going to smash a small galaxy into a big one. And I actually prepared the actual code that you would write or in the script or on the terminal. And what you want to do is make these things called shell galaxies. And you do that by creating a small galaxy that you see at the bottom left over here. I don't know if my mouse is visible, that guy. It's 2% of the mass of the big guy. They're both plumber spheres, if that means anything to you. You smash them into each other so that they will merge, so not too fast. And as it plunged back and forth and merges, it's like you throw a stone in a pond, it produces these ripples, these caustics. And another thing to note, in this particular thing, you have these wings far away out. You don't see those wings in reality. It's possible that there is not enough dark matter in this particular galaxy. In this case, they would escape. Well, let me go over what you see here. We created a plumber sphere in this particular file with 100,000 stars and a seed of 0, so we get a different galaxy each time. So that was one example. Then the second galaxy that we make, we do the same thing, but we don't specify the file name. We put a dash there, so it goes into this pipe that you saw. So you pipe it into snap scale. That scales the snapshot with a mass ratio of 0.2. And to keep the galaxy in virial equilibrium, the R scale has to be the square root of that number, and the velocity scale has to be the quadruple root. So then you have these 2 files, number 1 and number 2 here. You stack them on top of each other. Number 1 and number 2 goes to number 3, and then you separate them by a spatial extent of 10 radii, and you approach them with a velocity of minus 0.07. Along the x-axis. The units that we use here, unlike some more modern tools, are virial units or n-body units. So you have to scale your problem later to, is this a galaxy, or is this a globular cluster, or is this a planetary system, let's say. We use Walter Danin's code, tree code, which is one of the fastest code that we have in NEMO, to go from number 3 to number 4, and we integrate to a time of 100. And think of that like dynamical times, crossing times, whatever. Then we take that particular number 4, we put a grid on it between minus 32 plus 32, and that is what you see below here. Here you see an example of these expressions. The emission variable is 0 for particles less than 100,000, and it has the mass for less than. So you get this particular frame over here. And then you create a FITS file. So let me now go, let me go to the terminal. I have to do something magic to get NEMO loaded. Prepared a little demo in run 701. So this is part of a bigger script. We had a special script that runs lots of these simulations, and we always keep a little parameter file to remind ourselves how we ran this particular simulation. So that number 4 file that you saw is over here. So that's the whole simulation. And I need to remind myself, mstat on run 701.4. And I want to give it that keyword because it found 2 types of masses, and I want to give them each of these masses a different color. Otherwise, they would all get the same color. So that is not stored in the file, the color. I have to give that specifically, in this case, to GL-NEMO2. So this is this visualization program. To make it larger, we get a little reference frame here. I'm going to turn that off and start the simulation by clicking on this. It went very quick, but you can see these shells that were formed here. You can see that these extensive things here in this outflow. If I decide to go here and just look at one component, this is obviously galaxy number 2, the intruder. If I look at the other one, I can see it doesn't have that structure at all. It looks like an unperturbed plumber, except you see it's actually not centered at the origins. It's a cool tool in GL-NEMO2 where you drag a little area, and in that area it finds the center of mass. Oops, why didn't it work? And then I have to zoom out again, which is similar what Alex just did. But now it is centered at that particular galaxy. So if I go back to this one, there's a bunch of tools in here. There is also an option to do orbits in here, as well as you can assign velocities to, velocity factors, which I don't think I can do easily here because I don't know how to scale this. But anyway, this tool also has an option here on the left where you can make movies. You have a whole interface to movie making. The generic use that you just saw me use is fairly easy for beginners, but the interface to make movies and so forth is a little more challenging. But Jean-Charles, my collaborator who wrote 99.99% of this program, created some really good YouTube videos, and you can just go on YouTube and Google for GL-NEMO2 if you want to use that. In terms of files, you saw that it reads a NEMO file, but it can also read a bunch of other formats like a number of embody formats that we have, and so that's described in his manual.
Peter, 1 minute remaining. 1 to 2 minutes.
That's very good because I'm done. I am done. Yeah, so that was it.
Okay.
I don't have any other slides. The rest
Sorry,
is
I didn't mean to
slides
cut
here.
you.
Yeah.
Okay. Yeah. Okay. I didn't mean to cut you off.
No, I was done, really.
Okay, awesome. If we don't have clarifying questions, we can move forward to Catherine. Thank you again, Peter, for an excellent talk on NEMO. And I love NEMO's acronym. I did not know that was the full form. So yeah. So let's open up for questions.
Yes, and just so everyone knows, if you have any lingering questions from either of our talks, or if you come up with one while we're having our little discussion here, please feel free to throw those in the chat. I will be sure to be looking for them. Is your hand up, Amrita?
Yeah, for questions.
Okay, great. Yeah, you can go first then. Be my guest, please.
Okay. So one question I had for Alex was, you had mentioned that as long as you can get stuff into a dumpy array, you would be able to load it in Firefly. But like if you're trying to take in some of the large data sets from surveys like Gaia or ZDF, are there limitations to the data sizes that we can, use?
Yeah, so what we found is that something like 20 to 30 million points is the upper limit where you can load the entire data set into Firefly. But we have this progressive rendering scheme where you go through a pre-processing step for extremely large data sets like Gaia, and you sort it into an octree. So you actually spatially resolve it and index it into chunks. And then once you've done that, I mean, you know, the most we've tested is 1.5 billion points. But in principle, you know, as large a data set as you want, because as long as you're able to run the octree generating algorithm, which I tried to write with a moving memory window and everything. So everything should scale. It's all parallelized for extremely large data sets. And maybe I can answer one of the questions just briefly that I saw in the chat as a tag off of that. For Gaia, it took me about half an hour to run on a single core with like, I think it had like 50 or 60 on a single node with 50 or 60 cores.
So Alex, if I may ask a follow-up on that, when you said you build an octree and so forth, is that written in JavaScript inside of the browser? Where is that written?
No. That's happening in Python.
Yeah.
And
oh, in
so
that secret file that you wrote.
In the PDPP, yeah, what it
Right.
takes is you give it the data as NumPy arrays, or you can describe it like where it lives on disk, and then you have like a moving memory buffer that will open up pieces of it and then generate an octree, and then it will output to disk nodes of that octree, and then also make a JSON file that describes the octree that's read in to the JavaScript, and then the web app walks the octree and then loads just the chunks that are in the camera's frame of view. So to answer your question, Amrita, if you have these really large, extremely large data sets that you can't get into a single NumPy array, there is a framework for building this more generalized data structure to be able to load it in chunks seamlessly.
Is that Dask by any chance? Is that in
I
Dask?
do not use Dask. No, I wrote it all myself. it's I think I don't even think I use Numba. I think it's all pure Python.
Oh, wow. Sorry, I was assuming. Anyway, great. Thank you. That's very, very interesting. Unless we had other related questions related to just kind of dealing with large data sets, things like that. We had one other question in the chat for Alex. Yeah, great. Yes, someone asks, can you apply Gaussian profiles to the particles to make them blur when you go to visualize it?
Yes, that's actually the default. I think in all the examples that I showed, we were color mapping at some level, which you can't have transparency and disable blending, because then what you end up with is stuff that's being blended with a background. You get this weird black halo around all the particles. So yeah, the default is to have like kind of the fuzzy edges when you're just showing like a single monochrome color for an individual data set.
And same in GL NEMO too.
Yeah,
it's an option. You slide the
yes,
size.
yeah.
There might even be an option where you assign the Gaussian blur to a variable in the data model.
Like the radius. Like
you assign a variable like smoothing length or whatever, and you can apply that to that. It depends on the data model. I'm not so up on that. A cute thing about GL NEMO 2 is it also reads Fitz cubes, because it just assigns a particle to each voxel in the cube.
Sure.
And then allows you to, that's really cool for looking at radio cubes. Oh, so my question wasn't really answered yet. That large Gaia data set that you talked about, you have to do some work on it to create that PDPP file. What is the typical timeline I'm looking at? The real question is really, if you have a terabyte and my disk is 100 megabytes per second, do I get a speed of 100 megabytes per second and that's the time, or is there some overhead in CPU that you need?
I mean, there's some overhead. I mean, it depends on how. Yeah, I mean, I guess, like I said, when I did the whole Gaia data set, which I think was something like 500 or 600 megabytes or gigabytes, 500 or 600 gigabytes. And that was just the position, velocity, and like maybe 3 or 4 like BP minus RP T effective type scalar fields. I mean, the vast majority of the time is spent building the octree and organizing it on disk, which is optional only if you have these like extremely large data sets. Actually writing out to binary, yeah, I mean, it should go very, very fast. That's yeah, I mean, I imagine the limiting factor is definitely going to be your disk write speed.
Yeah, we have this same problem in NEMO that you sometimes memory limited. So you can recompile NEMO and assign floats as opposed to doubles, which is the default. And your body is normally, let's say, 100 bytes per particle. But if you want to have more trimmed down particles, you can go down to maybe only 6 phase space variables. So in your case, if you load a really huge data set and you don't care about the velocities, is it possible to use a data model with just X, Y, Z and really trim down memory?
Yep. Yeah, the velocities are all optional. I mean, you don't have to necessarily put in velocities. You could put any kind of vector data to show.
Right, but you do save the memory when you say, I want a data model that just has the...
Yeah, I don't just save like a bunch of zeros or something. Yeah.
Thank you. I think Amrita had a couple other questions. Yes?
Yeah, so I don't want to monopolize the whole Q&A time because I know we have a lot of members and it would be great if they ask their questions as well. So one quick question I had was, have you tried also combining some of the multi-wavelength observational data sets? And, you know, if we can also use all of, for example, I was thinking of a specific case of if it's an accreting X-ray binary and I have data in optical and IR and UV and X-ray, can Firefly handle all of that together?
I mean, I think it depends on exactly what visualization you want to make. I mean, certainly you can input that data as like separate particle groups or something and toggle between it or do whatever you'd like. But if you want to do like a false color RGB image, we're like 3/4 of the way through that sort of projection remapping implementation. So I have some separate software code that will make like mock Hubble images of simulation data. And I'm like I said, I'm about 3/4 of the way through getting that running live. And it's the same idea of you project through, you have your 3 channels, you apply some transfer function and remap to RGB space.
Yeah. Okay, cool. I would be very interested when that is up and running.
Thank you. We have another question in the chat. Andrew asks, for Firefly, is there any option for hover tools for interactive querying of the values of scalars for a given point?
Simple question, simple answer, no. No, it's something we really, enough people have asked that we know that we got to do it. And it's just the sort of thing that we got to sit down and we got to do. It's on our milestone roadmap, but no.
I saw in Jean-Charles' videos that he does have a way of labeling pictures and not only pictures, but also particles. But obviously for a billion, you don't want to do that.
Yeah, we have a couple of ideas of like you can denote like points of interest, maybe where there's like a subset of the particles that you want to label like this. We also have ideas of like how you might select like a group of particles and give some summary statistic, like the total mass in your like little sphere or whatever. But if you have a small enough number of particles that you care about individual properties of them, then we should let you have a hover. Like we should, but we don't.
Yeah, I think for him, it was more like you have a post-processing software that does groupings, assigns the group. This is group A, B, C, and then you have it creates a little structure in GL-NEMO 2 where you see where A, B, and C is.
Great. If we had nothing else to say toward that end.
I think Alice had one quick question.
Oh yeah, no, that's what I was moving on to that. I just wanted to make sure I didn't trample the previous conversation. Yeah, so Alice in the chat is asking Peter, what are the future plans for NEMO?
Oh, gosh, it runs itself. We have enough issues on GitHub to keep us busy and questions. In practice, I wind up using NEMO a lot in my radio pipelines at the tail end to do some analysis. So that has always needed some patching, and new ideas come in that way. So I don't have any great future plans, maybe a little bit more with Python. It's always tricky to find the right balance where you stop computing with compiled code versus Python. That's always tricky.
Thank you.
Absolutely. Yeah. If there are no other computer science modeling questions, I have someone requesting to know more about Alex's dog.
Okay. You got spotted. You got spotted in the background.
Oh my God.
Oh,
This
that is
is-
so cute.
This is Pepper. She is my baby. We just had her for 2 years. Last week was our adoption day, and she is a Basset Hound and a
Oh.
Rhodesian Ridgeback. She looks like a 65-pound wiener dog. But she is not actually a dachshund.
When you
She's
picked
very
her up,
sweet.
my first thought was that is the largest wiener dog I've ever seen.
Yes. She has a very long body but very short legs. And she tolerates being picked up very well.
No, hi Pepper. Welcome to the community.
Well, thank you
Um,
very much. Yeah,
yeah.
Amrita, do you wanna-
Yeah. Thank you all for joining again. And let's give a big round of applause for both of our speakers, Alex and Peter. Thank you for joining us today. And we will have the recording available on YouTube soon.
Thank you
Okay,
for the
see you
opportunity.
next month.
Mhm.
Yeah.
Bye.
Thanks,
Bye.
everyone.
See you
Thank you
next month.
all.
Bye.